As energy consumption increases,
cheaper energy sources are needed.
One energy source uses nuclear fission, meaning an atom is splitting apart, releasing energy. I'll be talking about the fission of uranium-235 specifically. In order to split a U-235 atom, we need to destabilize its nucleus. We can do this by shooting a neutron at the atom, and after the atom absorbs it, turning it into U-236, which is unstable. One of the ways an atom can split is into a barium atom, a krypton atom, and 3 more neutrons. So how much energy does one U-235 atom release when undergoing fission? To find out, we use the mass-energy equivalence relation, E equals mc squared. We can get the energy difference by finding the difference in mass before and after fission. We know that the mass before is the sum of the mass of the nucleus and 1 neutron, which comes out to be about 236.05 atomic units. The mass after is the sum of the baryon and krypton atoms and the 3 neutrons, which comes out to be about 235.87 atomic units. So the difference is about 0.19 atomic units. 1 atomic unit converts to 931 mega-electron volts over the speed of light. So the difference in the mass converts to 173 MeV over c squared. And after this c squared cancels out, we get that change in energy is about 173 MeV, or a very little amount of joules. This may not seem like a lot, but it's only 1 atom, and there's a lot more than 1 atom in uranium fuel. The 3 neutrons from the atom splitting will hit other atoms and continue the chain reaction.
Fission reactors have fuel rods encased in water. Fission occurs in the rods and heats the water, turning it into steam. That steam turns a turbine, creating electricity. The leftover steam is then condensed. This can happen in a cooling tower that releases waste heat. In order to control the reaction, control rods made of material that can absorb neutrons easily, such as boron, are positioned in between the fuel rods in order to absorb different amounts of neutrons depending on how far it's inserted, allowing control over the neutrons that pass between the fuel rods and therefore the rate of the reaction. Some reactors have a secondary feedback loop where it heats coolant and uses hot coolant to heat the water in a second loop. Since the heat has went into the water, the coolant returns to the reactor. Fission bombs contain 4 main parts: the shell, the fissile core, explosive lenses, and a trigger. When the bomb activates, the explosives go off and compress the cores down, increasing chance of fission as the neutrons are more likely to hit core atoms. After the core is compressed, the trigger, which can be neutrons from a neutron source, or a piece of material about to undergo fission. There is a lot of complications with the timing, however. After the trigger hits the fission core undergoes fission very, very fast, which releases energy very, very fast, and that creates an explosion.